Hi, this is a quick look at the Cypress analog coprocessor kit. It has a number of sensors and it has a PSOC, which is programmable system on chip. The PSOC is basically Cypress's flagship product, and they say that you can configure each pin as, for example, they have analog multiplexing and stuff like that happening inside. You just draw a schematic and then you can use each pin as, for example, an op amp, or you may use the same pin as a analog to digital input, or you may have a gain op amp wherein you can set the gain to 1, 2, 10. There's a limitation to the amount of things you can do, but it's quite extensive. In this particular kit, we have a number of sensors which are resistive, capacitive, and stuff like that. The objective here is to demonstrate how easy it is to interface such sensors with the SoC associated with this product. Now, my objective here is to use the PIR sensor, the temperature, the humidity, and the ambient light sensor, all combine them. And of course, there is the demo project available on the Cypress website, but I'm not going to use that. What I've done is I've tried to experiment with it. This is the first I've installed the PSOC Creator software, and I'm going to experiment with how to create a project with this thing. So we'll actually deal with the software and the hardware. Let's take a look at both of these things one by one. All right, let's take a look at the hardware. The hardware basically has two segments. So this part over here, this is the bigger PSOC 5 LP, which is used as a programmer as well as a bridge. And we'll take a look at the software part. This is really interesting and really good, actually. The other part is this little thing. This is the PSOC analog coprocessor. It has that analog functionality like operational amplifiers, ADCs, and then a Cortex M0 Plus processor on board this little thing. It's a 48-pin QFN package. In addition to that, we have the sensors here. So these sensors are already connected to this little chip, and this little chip talks to the 5LP, which is again another PSOC, but it is used to program. And so this kit can be individually used as a programmer as well. You can use this for separate projects as well if you want to do that. Let's take a look at the schematic of this thing as well as the hardware diagram, and then we'll take a look at the PSOC software itself and how to configure all of these sensors, how to read all of these sensors. Then the last part would be to read the software. And then one of the interesting things that came to play was that the I2C configuration for this thing was quite easy. In order for me to exchange information between the board and the PC using their own proprietary I2C, easy I2C, that intellectual property core, and allowing some little software functions to copy data into a buffer and then send that data to the PC. And it was actually very easy to do. I was actually very impressed with that functionality, because normally when you use an Arduino or something, there's a lot of send a start bit, and it doesn't need to do all of that. You just drag and drop some stuff. We'll go through that, and let's see what's inside and how to program this thing. All right, so I am using PSOC Creator 4.0. As you can see, I've already opened up the design. This is I've already installed the kit files that actually came as a part of the package for the Cypress Pioneer kit for coprocessor, the analog coprocessor. So there are 1, 2, 3, 4, 5 of these project demos that are available. I've already opened the PIR sensing, and you can see that the blue wires exist on the analog coprocessor Pioneer kit, whereas these blocks, these amplifier stages, these references, and this counter and the ITC module, these are the modules that are actually available on the chip itself. So how does this work? Well, you have something called a component catalog where you can just drag and drop. For example, I want to drag a digital constant or a virtual multiplexer, or maybe something like a port pin, analog pin, digital pin, stuff like that. Just drag and drop and you get that. In addition to that, you have these blocks such as the ADC, the SAR block, and the amplifier block, the op amp. Here you can see if I double click this op amp, it gives me the programmable gain amplifier, or the PGA. All right, so you can you set the gain to 1 all the way up to 32. So the power bandwidth, you can set basic different parameters for the operation amplifier. When you click the data sheet, you get this big information sheet. You can this is a programmable gain amplifier, buffer high impedance sensor signals. What are the features for this thing? There's a laundry list of things you can do here. So you can set the gain, different the reference pin, the output, the deep sleep operation, where it'll really consume very low power with reduced power and performance. So yeah, there's a lot of stuff actually available with all of these components. Now, what I've done is I've started off with this PIR project, and I've gone ahead and modified it. So this is my final design, wherein I have the PIR segment. In addition to that, I have the CapSense module, which basically is used to detect the humidity using that capacitive humidity sensor. In addition to that, there is my ALS, or the ambient light sensor. Then there is the thermistor, and you can see that the scanning ADC has been modified to include 4 channels instead of the single channel. So 1, 2, 3, 4. I've had to move some parts of the design. For example, this LED, the thermistor calculator, the I2C, the easy I2C module onto the second page. So my schematic is basically 2 pages, and when you hit this build button, it builds this entire design, and it puts it into an HDL file, and it generates the APIs. So Workspace Explorer shows you all of the different files available. So this is the capacitive sense stuff, the boot code, the I2C code. And one of the wonderful things about the I2C module is you just drag and drop. You don't have to worry about the pins and all that. Of course, you can modify it. Taking a look inside the design-wide resources, if you double click on the pins block, you can see this is the actual chip, and you can really configure this. For example, I'm using these 2 pins as pin 4.0 and 4.1 as my I2C pins, and you can really modify these. There's a limited set of lines that you can use. So I can use 40 and 41 as well. So this is 5.1 and 5.2. No, okay, so you can use all of them. Pin 3.0, where's 3.0? Hold on, there we go. So I can use these 3.0, 3.1 as my lines as well. So you can see it says I can't do that because restricted function block. You get the picture. You can modify some parts of it. You can modify all of it. Hold on, I think I can modify both of them if I want to. 3.0, so I want this to be 3.1. Can I do that? Okay, so that works out. There we go. So I can move both of these clock signals from these 2 to these 2, and the design will build. In this case, I just want it to be 4.1 and 4.0, and this should work out. 4.1, 4.1, 4.1, 4.1, 4.0. And yep, it resolves itself. So there are some port pins that are actually not being used. These are the debug pins. These are for my thermistor. These are for the PIR sensor. This is for the light sensor. And these capacitive sense pins are for the the humidity sensor. So once you have this, I can then go on to modify my code. So you just go into main.c. This is a heavily modified version of main.c. So this is my project while you were away. This particular project is for a submission to a Hackster.io design contest. So we'll go into the details some other time. You can see you just have to create some functions for the capacity. I've just copy pasted from the 5 different projects, and you can see the main has most of the code that was that came with the demo, and I've just merged them all together. So what the ADC convert, thank you very much. So you can see in this code that I'm using a function called isEnd conversion for the ADC, which basically means that the code runs, this function checks whether the ADC has finished conversion, and that basically means it's converting for all 4 channels. In case of Arduino, normally what you have to do is you have to run a function like read ADC or read pin, and then it'll give you the result for that particular pin. In this case, if you take a look at this last function, this is the init resources. And so it's initialization of all of the available blocks. So you can see I'm initializing the I2C block, and this is for the PWM or the ISR block. This is the ADC, and starting the ADC and then starting conversion. We'll come back to this in a minute. Once you start this function, ADC start convert, it converts for all 4 of the channels, keeps on converting it, and stores them in their individual buffers. Then we have the reference buffer, the PV reference. This is my voltage reference. I have to start that as well. Then this is the reference enable. Then this is my amplifier, that one gain amplifier. This is a programmable gain amplifier. You have to start that using a function. This is the gain stage 2, and then the op amp that I'm using, I have to start that, and the capacitive sense module. So there's a start function for all of the modules that you use in your design. If you take a look at this, I have to run a function start this, start this, start this, start reference buffer. So that's hold on, that's this reference buffer start. So you have to start this op amp. That's a bit convoluted to me, but I guess it's a system for Cypress. I'm not exactly sure what's the logic behind it, but okay, start this, start this, start this, start all of these modules, and you're like, you can maybe you can stop them and save power or something, maybe, I don't know. Then once you're done with that, every time you have to call this function is the end of conversion. Now you might be thinking, you know what, this is like a different way of writing code. You could just run a conversion once and then save all the results and do the processing. Yeah, but then when you have the conversion happening all of the time, so it's better to have the latest conversion results rather than use stale results if some of these calculations are long, or maybe it takes you know, something takes a lot longer to process, and then you have stale readings. So I just, since the ADC is converting, all I need to do is just check whether the conversion is completed for, say, the ambient light stuff, and then I get that results, the ADLS channel. And I've already created macros for that. So there is a PIR channel, that's 0. This is my reference channel, part 1. My thermistor channel 2, and the light sensor channel 3. The capacitive sense is happening in different functions, and these are the 2 functions. I've already copy pasted these from the demo code. I have no idea what they're doing, but yeah, okay, it's sensing some capacitance. It's using some kind of formula to calculate it. It's okay if it works. Right now the concept is to get off the ground as soon as possible. So there is a section for all of them, and at the end of each section, calls the function enter critical section, which in RTOS terms would probably mean that it's disabling all the interrupts. Then it checks whether the I2C bus is active. If it's not, then it will update the variable in that buffer, and then exit that critical section. Now, this to me was a very good thing, because in normal I2C terms you have to do a couple of things if you want to send data via I2C. Here all you have to do is just create a buffer. If you take a look at the init function, there we go, the init resources, all I have to do is say start I2C and then tell it that I have an I2C buffer, and that's about it. And it basically uses that structure to stored data, and whenever somebody from the external world accesses I2C bus and says, hello, I want this byte of data, it'll just pick up that data from the buffer and pass it along, and there, everything else, what the mechanics of it are opaque to the user. I don't know what's going on in the background, but it works, so I'm pretty confident about it. So that's something really good. Then this is my structure. I've defined this pack structure, which has all of these parameters that I can pass on via I2C from my board to any master device, such as the PC, or it may be a Raspberry Pi, or it may be an Arduino, and yeah, that's about it. So just a quick look at the code. I'll just step through it. Just starting with my project.h. These are my macros. I've already exported into to a different file. Prototypes. This is my buffer of initialization for the I2C bus. Some local variables all the way from start to end. Then interrupts enable for the PSOC chip. Calling the start resources, init resources function, and then my infinite while loop or for loop. Check this if somebody is actually send a command, because the PIR code actually has the capability for you to send a command saying, you know what, I don't want the detection to be this much, I want the detection to be higher, and the way it's achieved is by setting the gain of the preamplifier stage right here, this one. So you can set the gain in software, so you can send a command, change this gain from 1 to 2 to 5 to 32 all the way, and you can have a PIR sensitivity increased by that much amount. Anyways, just that's about it. Then I have the PIR conversion, checks for the PIR values. What's the previous value? Is it greater than the threshold value? Set an alarm, set the LED, and then update the buffers. All right. Then we have the similar function for ADC conversion for the ambient light sensor. Similar interrupts, store the value in the buffer and close that. Similar function for the temperature measurement for the thermistor. The code is basically copy pasted from their demo. And the last is for the capacitive senses. The capacitive sense scan busy. Is it not busy? Okay, it's ready. Then just call that function. These are the two values, and these are the two functions that I don't know what they do. I've just copy pasted them from the demo code, and that's about it. So that's simple. That's not too much. Just running this small short piece of code, and you have the entire project working. All right, let's connect the board to this thing, and let's see if we can get it to work. All right, I've gone ahead and connected the Cypress PSOC kit, Pioneer kit, and it's already connected to the machine. The drivers installed, everything is fine and dandy. Now, in order for me to get that data, all right, so let's take a look at my macro. So this is the function that is, so the first byte is going to be detection distance, which I can update using an I2C command. I'm not going to do that. Then there is the sensor raw value. Then there's this motion detected, all right. And then there's the temperature value, the voltage across the thermistor, ambient light value, so on and so forth. With the Cypress PSOC Creator, you get something called the bridge control. And the way it works is, once you plug in the board, it automatically connects to it. You can see it says connected I2C SPIR X8 ports, connected, powered on. Now, the way it's gonna happen is I want to read stuff. So it's the first character R signifies a read operation. 08 is the address. Here, let's take a look at that. I2C slave, and there we go. So the primary slave address is 0x08. So it's the 8 is the address of my board. Then an X is for 1 byte of read. So 1 byte, 1 byte, 1 byte. So if you take a look at the structure, you can see 1 byte, 2 bytes, 2 bytes, 2 bytes, 1 byte. So 1, 2, 3, 4, 5, 6, 7, and the 8th is motion. So 1, 2, 3, 4, 5, 6, 7, and 8. So how you do this is you go into the chart menu, variable settings, and you create variables. One is for motion, illumination, the current, temperature, the voltage, RTH, humidity, and you can set the sign if it's available, the kind of variable you use. For example, this is the unsigned integer 8, 1 byte, so unsigned integer 8 byte, so no sign bit here. Then you can use the at motion, and it will copy the data when it performs a read operation. For example, if I click the send command, so it's returning yes, 08, acknowledge, 03, 04, and you can see that this comes out to be 00, which means motion is not been detected. Let me put my hand in front of the PIR sensor. Now my hand is in front of the PIR sensor, and once that happens, you can see that it's now motion set to 1. Then it's since my voltage across the thermistor VTH is 2 bytes, so it's the 0th byte and 1st byte. So that means it's a 2 byte variable, and 0 byte and 1 byte. And this is kind of counterintuitive, but it kind of works, so I'm okay with it. So I'm one variable VTH, one variable RTH, one variable for temperature, one variable for current, one variable for illumination, 4 bytes for, let me see, 4 bytes for humidity counts, capacitance, and then this is the humidity. And the humidity is again 2 bytes. And I don't want to read the raw counts, reference, capacitance, so I'm just leaving that. And a P means acknowledge. So you can run this over and over again. If I send the command, I'm getting no motion detected, and really you can make a lot of sense from a lot of this stuff. So just going to click into chart and then repeat. So what it's doing is it's repeatedly running the same command over and over again. If I put my hand in front of the PIR sensor, you can see that the red line just popped up. That means the motion has been detected. All right. In addition to that, the illumination is this blue line. So if I wave my hand in front of the sensor, you can see the illumination goes down while the PIR sensor just detected my hand. If I take my hand away from the PIR sensor, 5 seconds, 4, 3, 2, and 1. There we go. And after 5 seconds, it goes down, and the illumination is pretty much constant. Let me just switch on a lamp. I've just switched on a lamp, and you can see, whoa, there we go, the illumination just popped up. And switching off the lamp, and that's gone down again. The same way you have humidity, there is, there's a plot for everything. So that means this tool is actually pretty nice, but what we need to do next is, instead of using this bridge control, I want to access the same data using an Arduino. So the next exercise will be, instead of using this, let me just stop this, instead of using this control panel, now what I want to do is I want to use the same 2 pins. Now the pins that I am using are pin 40 and 41. So I want to use these 2 pins to talk to my PSOC on this Pioneer kit, and I want to access that data from an Arduino. So that's something that I'm gonna do in the next video. For this video, it suffices to say that it's not very difficult to use PSOC Creator. I really I'm not I haven't really used all of the capabilities of this thing. I've just copy pasted it, but it was really easy to get off the ground, to be very honest. Didn't have a lot of things that I needed to do. You can see I'm using 4 interrupts. I'm using 19 IOs, segment LCD I'm not using, capacitive sense 1 I'm using for the humidity, 1 serial for the I2C, 1 timer to switch off the alarm, all 4 op amps. You can visually see that 1, 2, 3, and 4 operational amplifiers are being used up. So 2 DACs, like SARS, ADC. So it's pretty cool, actually, the way it's actually working. So I really liked my first experience with PSOC Creator. You can experiment with other modules, you can experiment with each of these programs, or you can go into getting started guides. This is a pretty deep tutorial series. There's a YouTube series by freetronics.com which you can go and watch, and I really recommend, if you are doing some analog or mixed signal stuff, you check out PSOC Creator and Cypress's PSOC offerings at least once. These kits are not very expensive. It's pretty good for the first timer as well. So we'll step into the Arduino domain in the next video, and we'll be talking to this board in the next video. All right, thanks for watching.